Hello and welcome to my project presentation forecasting Danube water levels. In the picture in the background you see a beach next to our home. I'm at home here in Spitz on the Donau in Austria, and the water level of the Danube is really important to us because we live literally next to the Danube. So what is the point here? Long short-term memory is a state-of-the-art machine learning algorithm, and I was wondering whether it can compete with the official government forecast for the water level that we use in living next to the river. So what I did, I downloaded the historic data for nearly 20 years from the government website. You see that on the left. On the right is a zoom in on the first year, 2002. You see the one peak goes over 1,000. That means water level more than 10 meters. And that means that in August 2002, the water was in this very house where I'm sitting up to knee level, so just below the table. Fortunately, the house was being renovated at the time, so we didn't have too much damage, but the Danube's water level is very important to us. So just a week ago, I did the IBM course Applied AI with Deep Learning in Coursera, and a dude there presented an application of the LSTM model for oil price predictions. I thought, that's cool. I want to try that with water instead of oil. So yeah, I just took his model configuration with the parameters and threw my water data at it. And you see on the left, doesn't look too good. The root mean squared error is about 73. And obviously, yeah, the prediction doesn't help anyone. I spent about half a day on tuning the parameters. And then I arrived at a configuration which looks reasonable on the test data set. And the root mean square error went down to about 40. So I thought, oh, pretty good. But then if you zoom in and look at the details, you see that the prediction actually lags behind a bit of the real development of the water level. So I thought, oh, I take linear regression as a benchmark. And surprise, surprise, the linear regression actually does better than the highly tuned LSTM model. So, well, I went one step further and also benchmarked the whole thing against a trivial prediction, which is just taking the previous day's value as prediction, and does also equally well as the linear regression and better than the LSTM. What do we learn from that? Yeah, you see the linear regression forecast overshoots a little bit. The LSTM stays below the real values, and actually the trivial prediction is better than the other two. River water level data seem to be inherently chaotic. So just trying to learn patterns doesn't seem to be very useful here, at least from this study. Well, what I can do, of course, is use data of different reading stations upstream and actually make a physically relevant model that takes a river as a graph and so on. But that's for the next project. So for the not so techy listeners, that's probably it. And now we'll switch to the code and show a bit about data exploration and what I did in there. So let's go to the code view. The whole thing was done in an IBM Watson Studio Jupyter notebook. So let's have a look at that. Of course, there are quite a few dependencies. So the model runs in Keras with a TensorFlow backend. And yeah, I'm just reading in the data file from GitHub. It's a small 190K text file. And it contains min, max, and mean data for every day. I used a few definitions from a Kaggle starter kernel for the exploration. That's quite handy. So the histograms, of course, look very similar because, yeah, the data are just the same, shifted by a day or so. They are also highly correlated, as one sees from the scatter plot. The max correlates with the min in one direction and then vice versa. And also the correlation matrix has all very high values. So since we're looking for float maxima, after all, I just decided to go with the maxima. So yeah, this picture you saw before, that's just the plot of the data. So yeah, next step was data cleaning. So actually there is one missing value in the data. So I replaced that by the mean of the two neighbors. And then the data were right to be fed in the LST algorithm. So the original parameter set, of course, yeah, test share also needs to be defined about 10%. And then 30 time steps, which corresponds to a month of data and a rather large batch size for LSTM. Some acrobatics of getting the data in the right shape. And then, yeah, here we configure the model. That was just the way the guy did it for the oil prices, 2 layers with first parameter 10, and yeah, running 30 epochs. But then you see already the loss doesn't really get down substantially over the epochs, and then yeah, we end up with what we end up, this picture with 73 loss. So I did some tuning, and it turned out that a very short window of only 2 days performs comparatively best, with also a small batch size. So again, the acrobatics on the data, and a much simpler model with only 1 layer, first parameter 3, and then yeah, 30 epochs, where you see that actually the loss goes down over the full set, at least up to 15 epochs or so, and then it stays put. And then, yeah, we get this better root mean squared error of about 40, and the picture you saw before. Yeah. And then for the linear regression, yeah, the same time steps, with different shaping, and then here we do the fit. The coefficients show it's just the value of the previous day with some correction from 1 day before. And yeah, here 33 as a RMSE, and the picture also you saw beforehand. So yeah, the trivial forecast is just the same data set offset by 1 day, and yields the result you have seen. One thing that wasn't shown in the presentation is the histogram view of the residuals. Also here one can see that they are rather comparable. Actually, the trivial thing really actually looks best. Yeah, and there we are. So if you have any comments, drop me a mail or comment on the gist file. There will be a link also next to the YouTube video. So yeah, thanks for watching. Have a nice day, and bye-bye.